So here I have a completely nonpolar molecule, electric field, nothing's going on. That's my evidence that it's nonpolar. But let's increase the electronegativity of B. So now we see some things happen. First, we have that arrow above. That's a vector. That's showing size and direction. And the arrow always points towards the negative, and the little plus sign on the other end is near the positive. That's one way of showing negative positive. A second way of showing negative positive is with that little Greek letter delta. The little delta plus means a partially positive charge. Delta minus means partially negative charge. They're not ionic. If I went like that, then they'd pretty much be ionic. But they're polar. The third way is through this color mapping. And the darker the blue, the more positive. The darker the red, the more negative. And for neutral, depending on the software, you might see green or gray. So this one, no matter how I turn it, I want to try to point it that way. I want B towards the negative. It's not going to happen because it's got a polar bond, and the negative lines up with the positive part of the electric field. Now let's take a look and see what happens when I go to 3 atoms. Reset. I'm going to set it this way. Atom A and atom C are less electronegative than B. And if I look at their bond dipoles, come on, go. You can see that there are polar bonds. They are both pointed towards B, meaning B is more negative, and A and C are more positive. I can do the same thing with partial charges, and I can see that B is more negative, A and C are slightly positive. And if I put it in electric field, it's rotating a little, but we're really not seeing much going on. But let's look what happens when I change the shape. As I move A and C closer to each other, you can see that the angle, those two vectors are not equal and opposite anymore. They're starting to both point towards B and not cancel each other out. So you can see the formation of that yellow arrow, the formation of a molecule dipole. So when I put it in the electric field, B is more negative. It points towards the positive. No matter how I try to orient it, that always happens. And the greater the angle, you can see the larger the arrow, the yellow arrow, the polar bond arrow, polar molecule. So if they're equal and opposite, not much happens. But the shape of the molecule matters. So now we have to not only think about, is the bond polar or nonpolar, but what about the shape? And in 2 dimensions, it's not that bad. People tend to be pretty good at it. But molecules are in 3 dimensions. which makes it even more complicated. So let's take a look at the notes. Take notes. I will send this to Notability. We're not really going to talk much about this slide. Linus Pauling in 1937 came up with the idea of electronegativity. If you want an electronegativity chart, which you really shouldn't need for this, but if you want the chart, here's a convenient place for me to put it. You really shouldn't need it because we know, according to the periodic table, that fluorine is the most electronegative. Cesium is way down here at the least. And we know the trend goes up that way. All right, again, this is mostly review. Nonpolar covalent bond between identical atoms or between a carbon hydrogen. If it's between carbon hydrogen, we're going to say it is nonpolar. If it's a hydrogen hydrogen, a fluorine fluorine, those are obviously nonpolar. If they are small difference between electronegativity, so we're basically going to say two different nonmetals, those are going to be polar covalent, with the exception of CH. So CO, CS, NS, NF, NH, OH. We're going to call those polar. And large electronegativity difference is ionic. So those are going to be between a metal and a nonmetal. Or the ammonium ion and some other anion. So I can have NH4 to SO4. That's ionic. There are no metals in there, but it's ionic because ammonium is an ionic cation. This should be review so far. And this set of rules that I'm showing you right here will simplify, and you really aren't going to have to go to that electronegativity table very often. All right. Take a second and write down why you think there's a bond polarity decreases as we go from HF to HCl to HBr to HI. Just write it in the margin. The valence electrons, which means the bonded electrons, are farther from the halogen, which I'll call X's nucleus. So less force of attraction. And if there's less force of attraction, then we don't end up with as negative an end, which means we don't end up with as positive an end. So dipole moment is an actual measurable thing. A bond is polar. It has a dipole moment. So we're talking about the same thing, but polar is the adjective, dipole moment is the noun. And a lot of times we'll just say it has a dipole. So if it has a dipole, we're talking about the noun. If it's polar, we're talking about the adjective. That's the difference between those two words. And a dipole is a measurable quantity. And they're measured in debye's, named after the guy who figured some stuff out. If we take a look at this, I don't want that little tail. If we take a look at this, we can see that the molecular dipole for HF, 1.82, HCl, only 1.08, because, as we just mentioned, that chlorine atoms' valence electrons are farther from the chlorine nucleus, so the bond is farther from the nucleus, less attraction, less polar. So vectors. Vectors have quantity and direction. So magnitude and direction. So for these simple vectors, it's easy to see what direction they go in. But sometimes life is more complicated. So let's say I have one going this way and one going this way. I want to know what's the direction of the polarity. Well, to figure it out, let's see, I will make just a little, finish the quadrilateral, the parallelogram. And if I finish the parallelogram and draw an arrow there, there is my net dipole. If I have 3 of them, like in my trigonal planar geometry, first I'm going to finish my parallelogram. Then I'm going to add my dipole. Now look, my green arrow is the same size it would be if I drew better, and opposite direction from my purple arrow. So now, having something in a trigonal planar shape cancels out all the polarity. It's nonpolar. So here are some common shapes that we look at. Linear, trigonal planar, nonpolar. Tetrahedral is a little tougher to see. There's a little caveat. In all cases, we are assuming the bonds are identical. If they're not identical, then they're polar. So if we look at water, we can see that water has polar bonds, and they're both pointing towards the oxygen, so we end up with a net dipole facing up in this direction with a dipole moment of 1.85 dBs. Water is about the most polar thing we're going to be dealing with on a regular basis, covalent molecule. If we look at ammonia, so here is my nitrogen atom. And I have one coming out towards us. One going back beyond the plane. And one right in the plane. My little lone pair is up on the top. My dipoles are all pointing towards nitrogen, so I have a net dipole of up. From the top view, it would look like this. So from the top, it looks like trigonoplanar. That would cancel out. But because these are all below, the 3 hydrogens are below the plane of the TV, we have and the nitrogen would be above the plane, we have a net dipole out towards us. And so it has a dipole of 1.47 dBs. So here are just some examples of polar and nonpolar molecules. So to figure out whether things are polar or not, one of the things we're going to look at is the dipole moment of the bond, but then we also look at the molecule. Helpful hints. Hydrocarbons are nonpolar. If it is just hydrogen and carbon, it's nonpolar. There are a few exceptions to that, but none that you will be responsible for knowing about. But if you compare CH4 and CH2Cl2, you can see that there's clearly a difference between the two. And this one has polarity going towards the chlorine atoms, halfway in between them. Another helpful hint. If you have an OH, that's polar. Every time. Same with an NH. But to a lesser extent. But if you have an OH in a molecule, you're going to have a polar molecule. Alcohols, carboxylic acids. Because there's a big difference, because oxygen is so small or nitrogen is so small, and those valence electrons are so close to the nucleus, it really pulls those electrons towards that more electronegative atom, meaning the hydrogen is left fairly positive. All right, here's another look at polarity. Look at that one. Yep. So the first four all have 3 carbons and an oxygen. These two, we have the alcohol and the ether. The O attracts the electrons, really pulls them away from the H. That's pretty polar. This is also a polar molecule, but not quite as much, because yeah, the oxygen really pulls those electrons, but it's kind of spread out through that whole bottom of the molecule is negative. So it's spread out over a bigger area. So yeah, it's polar, but it's not as polar as that little corner of CH3, CH2, CH2OH. Over here, where we have a carbon, which you can barely see because it's so dark, and a double bonded oxygen, that one's fairly polar. As is the one with the carbon and the double bonded oxygen at the end of the molecule. The first one is called a ketone. The second one is an aldehyde. We're going to come back and learn about those more later. But let's take a look so we can see most polar. These are also pretty polar. The ether is really the least polar. But once you put that oxygen in there and you end up with that bend because of the 2 lone pairs on the oxygen, you end up with a polar molecule. But it's also degrees of polarity. That's going to become important in the next chapter. All right, let's compare propanal, 3 carbon atoms, and octanal, 8 carbon atoms. You can see they both have this polar end, but having a polar end doesn't necessarily mean the rest of the molecule is affected. After you get through the first couple carbons, the rest of that oct part is non-polar. So we end up with a polar end and a non-polar end. Anybody know of any things that do that? Oh, you want to give it a try?
I forgot like the first part when that like some fatty acid or lipid.
Lipids. So in cells you have a lipid bilayer where the nonpolar ends are pointed towards each other. They also happen if we can turn fatty acids into soaps. And we're going to talk more about these in Unit 3. But we have a hydrophilic polar end, and we have pure hydrocarbon on the nonpolar end. The longer the chain, the bigger the difference. So what soaps do is they arrange themselves so that the grease is surrounded by the nonpolar end. The polar end is all outside, and the polar end and the water interact and it can be washed away. All right, so let's decide if these molecules or ions are polar or nonpolar. I'll do the first one, and then I'll let you try a couple. So the first step is to draw the Lewis diagram. So I have 8 electrons, and H, 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 H. I know it is not flat like a square. It is tetrahedral. NH is a polar bond, but all those polar bonds cancel each other out, so we have a non-polar molecule. And then for the one right below it, I still have 8 electrons. And the way I drew it was, it looks like those hydrogens cancel each other out. But the way I drew it isn't the way it really is. It's a bent molecule. And so those hydrogens don't cancel each other out. Let me pull up a picture of it. There it is right there. I have bond dipoles we can see. And I have the molecular dipole. So this is polar. So try a couple of these. Take a minute, see what you come up with. And I'm going to unshare my screen. Actually, I'm going to put this in front so you can't see it, so that I can write the answers up. All right, when you are done, you can look up and see my answers. My carbons in CH3OCH3 are tetrahedral, but I'm not really worried about that right now. It's really the bent oxygen that makes it polar. So let's take a look at a couple of these. CH3OCH3. Nope. All right, so there is my dimethyl ether. And I can look at my molecular dipole. Here's my bond dipoles. A lot of them cancel out. And again, I can look at my partial charges. My oxygen is negative. The others are a little more positive. The next one was SCl4. We'll do tetrafluoride, same shape. We can see it's got a seesaw shape. That's not strictly linear because remember the lone pair is a little bigger. And if we look at the molecular dipole, it is away from the sulfur towards the two center chlorines. The next one, wrong button. The next one was H2S. That's going to be like H2O. SEF6. I don't know if they have that one, but they do have SF6, which is the same shape. We can see that's nonpolar. Everything cancels itself out. And then the last one, right ion. We can see the molecular dipole is towards the oxygens. Questions? Because I've got about 2 minutes left. All right, so let's go back to this assignment. Where it says this interactive, that's the website I was just at. Homework, polar bonds and polar molecules. And then the other thing you're going to be doing before you take the test on Wednesday, Monday is a review, Tuesday you'll have more time to work on some other stuff, is what shape is the molecule. And that's the Play-Doh I gave you. I gave you Play-Doh, right? Okay. So you're going to build the Lewis structure, figure out the shape, polar or nonpolar. And it turns out all of these have two different types of atoms, so you'll have two colors. And they work better if you break the sticks in half, because if you want an atom stuck way out and it's too heavy and a long stick, it starts to fall, but in a short stick it won't. That's physics. So you'll build some models, you'll take some pictures, build some models, take some pictures, identify them. And so this is everything in the unit. This is a review of the entire unit. And then at the end, there's an old AP test question for you to try. Questions?